Hi there. Today we're looking at regularizing trajectory optimization with denoising autoencoders by Renu Bone, Norman Di Paolo, and others of various places, but a lot of the people are from Curious AI. And we actually had a discussion with Hari, who is the CEO of Curious AI, and this was on our Machine Learning Street Talk podcast. So this is another YouTube channel, for those of you who don't know, where every week or so we try to have either an interesting discussion or a guest, like sort of an interview, or comment on the talk. So if it is not out yet, I'll link to it as soon as it comes out. But if you're watching this video later, make sure to check out our conversation with Hari, because it was absolutely fantastic. And in general, if you like videos like this, consider subscribing, liking, sharing if you're still here at the end and liked it. Okay, so this paper on a high level deals with model-based reinforcement learning. Model-based reinforcement learning means that you are using a model of the world to do reinforcement learning. So in essence, if you have your reinforcement learning setup where you are an agent and you have to interact with the world, you have to do so in many steps in like a round-trip fashion. So you put an action, you act, and the world gives you back an observation. And you have to act in the world over and over and over, such that you will be able to maximize your reward. Now, what is model-based reinforcement learning? Model-based reinforcement learning basically means that the agent here has internally a model of the world. So it sort of understands how the world works. Situations where you have a accurate model of the world are things like chess. So in chess, the rules are very clear. You know how the world's going to behave if you perform a certain action. But in real world applications, it's very, very hard to actually make a model. So people usually rely on learned models. So what does it mean? You basically learn a neural network that tries to predict how the world is going to act. So this here is going to be a deep neural network that you learn from what you see in the world. Now, trajectory optimization basically means that you now have this world model and you use it to look ahead, as I said. So you are in the state like here, and you can do, let's say, 3 different actions. And you use your world model here, world, and you think, how's the world going to react if I do either of those 3 things? And then you get into 3 different states. And then again, after each one, you consider 3 actions. 3 actions here, 3 actions here, and so on. So ultimately, you're going to kind of have an overview over a planning horizon, which here we call H. You kind of look ahead a couple of steps, or there are various ways of doing this, but ultimately you will basically find that, this path here is really good, so I think I'm going to take this as a first action. So trajectory optimization considers finding the best green path here in this tree of possibilities that your world model gives you. Okay? Now, what do these people say? They say this procedure often suffers from exploiting inaccuracies of the learned model. What does that mean? That basically means that if I have a world model and it is not accurate, then it is basically the thing that tries to find the best green path here, the optimizer, is sort of trying to find the best path against this world model. Now, if that world model is inaccurate, that can lead to devastating consequences. So what do we mean by this? I'll give you an example. If you have a room, right, and the room is, let's take our classic room like this, and you are here and you would like to go here. Right. And so you're a reinforcement learning agent. You do some exploration, right? You explore a bit here. The next episode, you might go here and you might go here and so on. And over time, in this framework, you're going to build a model of the world. So at the beginning, we won't tell you how these rooms look. You have to discover it by yourself. So maybe at the beginning, we only tell you there's these 4 walls. The rest you have to figure out. So on and on, you're going to fill in your blanks. You do your first explorations and you think, there's a bit of a wall here, right? And there might be some wall here. I crashed into that, right? You go into here, you crash into a wall, you say, there's a wall here. And here, there's a wall here. You go maybe here, there's no wall. So you go further. There's no wall anywhere here. You crash here. Okay, we already knew there's a wall. Maybe you crash here. All right, so right now, you go here. You have a model of the world in this situation where there's a wall here, a wall down. And if you now try to do trajectory optimization, remember you have to go from here to here. If you try to do trajectory optimization, what is it going to turn out? It's going to turn out like, look, there you go. That works just fine. And that's not because you're so good at planning. I mean, you are good at planning, but because your model is inaccurate here, because it has never seen this, your entire training distribution that you trained the world model on only explored the area over here. Right? So you see how the more efficient this planning algorithm is, like the blue arrow, the thing that finds the blue arrow, the more efficient that is, the more consequential it is when your learned world model has mistakes, because it will exactly exploit these mistakes in order to get the shortest path possible, or the highest reward in that case. And this, they call this like almost an adversarial attack on the world model, which is a pretty good way of framing it. They propose actually to solve this problem. They say we propose to regularize trajectory optimization by means of a denoising autoencoder that is trained on the same trajectories as the model of the environment. We show that the proposed regularization leads to improved planning with both gradient-based and gradient-free optimizers. We also demonstrate that using regularized trajectory optimization leads to rapid initial learning in a set of popular motor control tasks, which suggests that the proposed approach can be a useful tool for improving sample efficiency. So, in essence, what do? They basically say, okay, we want to regularize this using a denoising autoencoder. And I think it's best if we look at the math for doing this. So, the math here starts off as follows, saying you want to learn a world model. This is F here. F is the world model. It takes in a state and an action, and it gives you the next state, or an approximation to it. And the parameters here indicate that this is some sort of function that you learn, like a deep neural network. You can do this in fully or partially observed environments. Now, when you plan, what you want to do is you say, I have a planning horizon H, right? And I have a reward function. And the reward function is going to give me a reward for each state action pair. Right, so if I'm in a state and I do a certain action, I'm going to get some reward. This could be you have reached the target, or this could be how much money you've collected or whatnot. So you're going to look a horizon H. You're going to look H steps into the future, and you want to maximize the sum of all the rewards here. So in the limit, this reduces to simply like, for example, reaching the target in our room's case. If H is infinite. But you can consider a lower planning horizon. So you want to find the action sequence that maximizes this reward in the future. Okay? And now this reward relies on your environment model. Okay? So here's the algorithm. First, you collect some data. Okay, that's how you start off. Then train the dynamics model, the world model, using the data you've already collected. Then for each time step t, you want to optimize this trajectory. So you want to find the best next action sequence and take the first action, implement the first action, and get the new observation. And you do this in a loop until the end. And at the end, you say add this data to D. So that's what you do. You use your world model to get the best action sequence. That's how you optimize the trajectory. And then at the end of the episode, you've done an episode, right? You went somewhere, you put all of this into your training data to make the world model better. Important to note here is that the world model will only learn about things that you have done, right? So there is kind of an interaction effect. That's the green area here. The world model only knows the paths. The world model only can accurately estimate the world where you have been. And that's going to turn out to be the entire problem, because this blue arrow finder can now go away from that. That's explained here. Potential inaccuracies of the trained model cause substantial difficulties for the planning process. Rather than optimizing what really happens, planning can easily end up exploiting the weaknesses of the predictive model. Planning is effectively an adversarial attack against the agent's own forward model. This results in a wide gap between expectations based on the model and what actually happens. Okay, and they have this example here where it's like an industrial control process, and what you have to imagine, there's like some sort of a container here with a liquid in it, and there are two pipes that lead to this container, pipe 1 and pipe 2, and there are valves here. So there's this valve right here, and there's this valve right here. So these are valve 1 and valve 2, and there is also an output pipe right here, and that's another valve right here. So you can control these 3 valves, the 2 inputs and 1 output, and you have to somehow optimize the reaction in here. So this is a chemical reaction made up out of the 2 liquids that flow in here, and you have to somehow optimize a property of that, and that's highly nonlinear and has maybe like time shift. So when you open a valve, it's going to take a while, and then it's very nonlinear, and then you are not supposed to break the pressure limit, so you have to also outflow some stuff. And if you just do this with a learned model, it looks like this. So first of all, here is a classic controller. Like, people have been doing this stuff in industry, and they basically build controllers for it. And you can do that, and that works out really okay-ish. As you can see right here, this is the product rate, what you're supposed to optimize, and you see some sort of a smooth, you're supposed to actually bring it to this dashed line right here. And this is some sort of smooth thing, right? And you're supposed to, I guess, bring the pressure here and the A in purge. I don't know what these quantities are, but you're supposed to bring them to the dashed line, and it's very nonlinear and very time dependent. So that works, and you see here kind of the smoothness by which the variables are manipulated. Now, if you just learn a world model and then do this trajectory optimization, basically this is some sort of a planning-based reinforcement learning with a world model. You see right here, it works, but it's super jittery. The pressure spikes here, and apparently this here is a pressure limit, so it spikes the pressure limit. And you can see that the manipulated variables are up and down and up and down and up and down, because at each step it basically completely overestimates its potential reward. It thinks like, wow, this is really good, but all it does is find a weakness in the model and not a really good action per se. Now, with their method to already take it away, you can see that now the control task super smoothly and very quickly converges to these optimal things, and you can see that the variables being manipulated are also rather smoothly manipulated, and that's an indication that the model is accurately estimating the rewards. Okay, so how do they do it? Via what they call trajectory, via regularization of trajectory optimization. So in essence, what do we want to regularize here? There are many things we could do to solve this, but the way this paper goes is they say we not only do we want the most return, we also want a high log probability of our taken path. So this here, as you can see, this is observation, action, and so on, observation, action. So this is the future. This right here is the future. So this sequence here is what is going to give me the reward right here, right? So G is also dependent on these things, but it's not said explicitly here. So G is dependent on your plan, or maybe let's not call this the future. This is the plan. Okay, this is the plan you came up with. So this is directly going to influence G, and G is the reward you're going to get under your model. But also you want the log probability of the plan itself to be high. Now, I think there is something missing here, and that is conditioned on your training distribution right here. And I think that's actually a rather crucial part. No, that's the KL thing. So this is conditioned on your training. So what you want is you want the plan to be basically in your training distribution. So you want your plan that you're going to execute, if that is actually part of your training data set, then you know, I have already executed this once before. And it's reasonable to assume that therefore my world model has learned from this experience and is going to give me an accurate reward. If we go back to our rooms example, then up here somewhere, if we go back to our rooms example, right, you see that anywhere in the green area where I have already explored, the world model is fairly good, right? It's going to give me accurate reflection of the world. But as soon as I go outside the green area, it is not. And inside the green area is basically where my training data is. Now, if I, in the future, actually take a path here, crash into a wall right here, right? You saw in the algorithm, at the end of an episode, I'm going to add my trajectory to the training data for the world model. So this green part here expands to include that. And now, if I go here again, if my plan goes there again, now I can trust the world model, but also now it is actually correct because it has a wall here. So you see that the regularization, basically, not only do I want the biggest reward possible under my world model, I also want that the plan that I'm about to execute has a high probability under my training distribution. Okay? And the way we do this is by denoising autoencoders. So you want the log probability here to be high, and you do this via a denoising autoencoder. What's a denoising autoencoder? A denoising autoencoder is basically, so if you have, for example, an image, and the image is of our trusty cat, Whiskers, and a denoising autoencoder is an unsupervised method where it's basically an autoencoder, so there's a bunch of layers compressing to a hidden representation, then uncompressing it again, okay? And at the end, you want to output the same as at the beginning. So it's basically an autoencoder. But the special part about the denoising autoencoder is that first you take your input and you put some noise on it. So that could mean anything here, but here what they do is they make some Gaussian noise on it. Now I can't really draw Gaussian noise here, but it would be kind of convolved with Gaussian noise. So I'm just going to add some noise like this. So noise. So there's some noise, you see, and then you feed that. That's now what you feed in here. And the algorithm is supposed to reconstruct this original image. So the algorithm is basically supposed to take away the noise. It doesn't see the original image, but it's supposed to produce it. And you do this with your training data. So what does that mean ultimately for our trajectory optimization? It means that if I have a trajectory that I did before and it maybe goes here, right? What I can do is I can make a noisy version of it, which would be the black one right here. So I put some noise on it, some noise. Right, it's kind of the same, but okay. And the denoising autoencoder is supposed to give me back the red one. This will simply give me some sort of a probabilistic model of my training distribution. So they go through the math here and show that these denoising autoencoders actually naturally output this log probability, the gradient of the log probability. Because optimal denoising theory says that for zero mean and Gaussian noise, the optimal denoising function, the optimal denoising function for zero mean Gaussian corruption is this thing right here. So it is, if you give me x and you tell me x has been corrupted by zero mean Gaussian noise of size sigma n, then the best, and you simply tell me, give me back the original image. The best thing I can do is to take what you gave me and add this gradient of the log probability of x, if I have a model of the log probability, right? So that's the best thing I can do. And that's the best denoising function. And now you have to think a bit in reverse. If we train a denoising autoencoder, that is going to approximate this best function that there is, okay? So we know that the best possible denoising function is this. We train a denoising autoencoder, which in the optimal case is going to converge to the best denoising function. So if we then reformulate and we do denoising autoencoder of x minus, or x tilde minus x tilde, that is divided by the standard deviation, the variance, that is going to give us this quantity right here, the gradient of the log probability. And the gradient of the log probability of x is exactly what we need to run gradient descent on our function. So here is our function again, g plus this regularization. Now they don't regularize over the entire future, but over these windows. But in essence, it's g plus the log probability of your plan. If you take the gradient of that, of course, you take the gradient of the sum. So it's the gradient of g plus the gradient of the log probability with respect to the actions. And here, simple application of the chain rule will tell you that you have to propagate through the input, through the x, and you need this quantity, the gradient of the log probability with respect to its inputs. Now, as we just saw, the optimal denoising autoencoder is going to output that thing. So if we train a denoising autoencoder and we suppose it reaches a good accuracy, then we can obtain this quantity basically for free. And that's the entire trick here. So in essence, what does it mean? In essence, what it means is that if we are in our room again and we have our partial model of the world, let's say we have this model, because we are here and all we've ever explored is, so we've explored these things right here. Okay, and this. Now when I go and do my trajectory optimization, and my trajectory optimization wants to go here, I simply say, no, I don't know that. I haven't seen that yet. You can only plan basically within the space where we have already been. So you can plan like here. So here. Now there is, of course, there is going to be some exploration, so some probability that you can go away a bit, but not too much, right? So in this case, it would result in the planning only to happen in spaces where we've actually been. So it might go here and then here because, okay, here we haven't been anywhere. But then that would lead me to take the first step in this direction and not in this direction. And if I take my first step in this first direction, then, of course, I'm going to be already a bit on the correct path right here. Whereas if I take the first step into this direction, then after that, I'm going to have to, once I crash here, I'm going to have to correct really hard. And that's exactly what's going to give you this super jittery control. Whereas if you only plan where you've already been, the probability that you're going to have to do like a 180 is going to be much, much lower. Okay. That seems like that's about it. Let's look at the experiments. So their experiments, basically, I actually want to go down here to this not the industrial control process, but to the Mujoko experiment. So these are kind of continuous control tasks. You might have seen it. So there's some, like one is the ant here is basically this 3D ant is like a blob, and it has, I think, 4 legs, and each leg has 2 joints, and it just needs to walk as far as possible or reach some sort of goal. And the half cheetah is like a 2D thing where I think it's something like this. It also has these 2 legs, and it's supposed to walk forward and not fall over. And you can put force basically on each of the joints here. So you see that their baselines are Gaussian processes, and this PETS thing is a previous baseline to also do model-based control with a learned model. And here their main one is the red one, and as you can see that it goes much faster. Well, it basically outperforms the rest in these more complicated tasks. And then card pole or something like this is lower dimensional, easier tasks. And you can see that at least it does not hurt. Now they say here something they don't show in the plots. They say that if you let this run for a while, then basically their method doesn't make any improvement anymore, whereas the baseline methods will sort of at some point surpass it. And the reason that is, and I'm not sure if it's on this exact task, but they mention that, which it's I respect so far, is because they say, since we only plan where we know. Is it up? Where did I draw it? Since we only plan where we know, we basically do much less exploration than others. We kind of stick to what we know when we plan. So inherently we do less exploration. And in our conversation with Hari, he basically said this is intended. And the intention is that you want to do your planning where you know, and then explicitly add a component that does exploration, so you have control over. So you can basically say, I've never been here, sort of. Now, you would be in an exploration phase, you would explicitly go there, rather than intermingle your planning with your exploration and basically rely on your planning to screw up and you're exploring. Because if your planning never screws up, then you won't explore either, right? Then you will always reach your goal, or your planning will always be correct. In these other methods that don't have this explicitly, they explore every time their planning screws up, and you don't want that. You want your planning to be as good as possible, and they do that by sticking to what they know. And then the next step, which is not in this paper, would be to add an explicit exploration policy to reach areas they've never reached before. Okay, so that's the reason why they don't ultimately reach the best accuracy, but they do reach the initial accuracy much faster than the other tasks, because they plan better. They have a long discussion here of what still problems are, like local minima or the planning horizon problem, open loop versus closed loop, compounding errors in planning, but I'm going to leave this out for now. And I thank you for being here. I very much invite you to check out the paper for more details. It's pretty cool, pretty easy to read, actually. It's written very well. And with that, see you next time. Bye-bye.